Okay, so this notebook is actually from Fast Core Notebooks. Um, it's still Fast AI, but there is a set of 4 notebooks which are in Fast Core, which form kind of the foundations of the library, if you will, where he begins to make changes to Python in order to enable support of the basic functionality of the library. So this is, we're getting into the nuts and bolts, pretty much the heart of the library, in at least key support for transform. And with that in mind, what I plan to do is, again, take a top-down approach in that we'll first yet again look at transforms and what they do and how they work, with using the tests that Jeremy has coded up in this notebook to check what transforms do and whether they work as anticipated. And then we'll back our way into the code of transforms, which then requires a Python meta class. And we'll kind of try to understand what meta classes are and how they enable us to do what we would like to do with the transforms. So this notebook has been heavily edited from what Jemmy has, both to add comments as well as we'll be making multiple passes through the notebook. So I've got comments like ignore for now. It basically says we'll start somewhere at the bottom, uh, run through the test, and then jump up to the top and go through it piece by piece, just to orient you. So after the exports, and I'll post this notebook once we are done with this session, but be aware that since the next part of this lecture, I don't anticipate we'll finish this lecture because it's quite detailed and involved, but even the next week, Sunday, is probably likely to be portions of this notebook along with type dispatch. So we'll be going back and forth through different sections. So,
Srinivas, excuse me, is this lecture 5?
yes,
Okay,
it's
this is still
lecture
lecture
5,
5.
but it may not be in exactly the same sequence. It's walkthrough 5 video, but for example, the data block, which we spent an entire lecture on, he just said, that's a tutorial on data block. Here is, he covered it in like 5 minutes and went on.
Yeah.
So given that, I mean, it's going to take us a while to get through this. And again, he refers to the testing at the very end, but I think it's worthwhile going through it in detail to really grasp what transforms do. We have done it once before, but I think making it current and bringing it closer to when we need to understand how transform is coded is very useful. So at the beginning, I have explanations for the class and stuff that we will back our way into. We'll just run the actual transform code in order to make sure that we can check and run the tests. So I'm just running these cells. We'll kind of come back to them and explain what they do once we have gone through all of the tests. These are again not necessary currently. So we'll kind of start here. As we discussed previously, I think it was 2 lectures back in walkthrough 3 or 4, that he explains the transform and does the live coding, and I kind of unrolled that notebook. So he recaptures what the main transform features are. And you can read in detail, so I'll just highlight some key points. The type dispatch is essentially the key capability that we need to code into transforms. But what it does is it dispatches depending on the input type that we provide, and it also casts the output type that we return. So that's, the details of that we will see shortly, but that's kind of what this type dispatch paragraph handles or explains. Then the handling of tuples. This is again slightly different from what he explains in the video. This is one of the things that's changed, which is all inputs to a transform are now handled as a tuple or a subclass of tuple. And so what that means is when you supply a tuple as an input to a transform, then the transform gets applied to every element of the tuple automatically. However, you can opt out of the behavior by passing either a list or Jeremy's version of a list, an L, because only tuples get this behavior. So it took me a little bit of time, and we'll see this in specific to understand what this really means. What this really means is that if you're passing in a tuple, then a transform automatically applies itself to every element of the tuple. However, if you pass a list or any other container, then you need to provide the code which is going to break up the container and apply the transform to every element in it. Okay, so that's the difference of handling a tuple as a default container, which means that it will the transform will apply, and we'll see, while this is all theory, we'll see it in practice just in a few moments. So if you don't quite grasp it, hold on and we'll see the examples. I'm just going through it since it covers it in summary here. The reversibility basically means that you can go back and forth through encodes and decodes. So for example, we have seen examples of, previously we've seen the normalization or standardization. You can kind of normalize an image and then you can go back to show the actual image. And that happens because we go back and forth between encodes and decodes. The important thing to realize though, and I think this has also been emphasized in examples and we'll see more of this, is when you call a transform, it automatically executes the encode code. For decode and setup, you have to do whatever the name of the transform, dot decode or dot setup. The type propagation. So whenever possible, the transform tries to return the data type of the same type that it received. And then depending on, there are ways that you can override it by providing none or by providing the specific type of output. Again, we'll see examples. The setup method, we have discussed this briefly and we'll see examples here. It just runs one-time calculations. This, for example, we saw in the standardization example was used to provide the mean and the standard deviation. And then there's another capability that's provided, which is the split IDX flag. And in fact, in the video, he refers to it as FILT or filter, but he subsequently changed it to split IDX, which basically says if the provided split index flag doesn't match what you have specified for the transform, then that transform will not execute on that input. So this is in order to be able to say, execute a set of transforms on a training split or a validation split or both, or control which portions of the split data you want your transforms to execute on. Ordering, we have discussed this briefly. You can provide an order to the transform, which then the pipeline uses in order to execute the transforms in a particular sequence. And we have also seen this use of appending new behavior, multiple encodes, multiple decodes, or adding new definitions of encodes or decode methods and for new data types using decorators. So there are multiple ways of defining transform. Each of these we'll see as we go down and look at the examples and the test. We've already seen 3 of these. One of them we have not, and we'll look at that in the test. We've kind of seen the case of extending the transform class, which is inherit from transform and then modify the encode, decode, and so on. The second one we have not seen, which is passing methods to the constructor. This basically means you can supply an encode function and a decode function to a transform class, and as encode and decode arguments, and then the class uses those functions for encode and decode. This is an example we have not seen so far, but we'll see it today. And of course, we also have seen the @transform decorator previously, and then passing a function to other transform-aware classes. They automatically, and I've emphasized this before, a pipeline or a transform dataset automatically transforms every function that's passed into it into a transform. Okay, so ignore some of these, and then here is where we begin to kind of look at the what a transform does and how it operates. We've seen examples of this, but again, going through the details. So if you don't understand any of what is happening, chime in and ask questions. I'll just go through the code, because executing the code essentially means, because these are test equals and test equal types, that it will just return when it returns with no errors. That means it's passed successfully, but I've added comments in order to explain what's going on. So here you see what's happening is the fact that we have defined a transform. Basically, it's nothing other than A as inherited from transform. Therefore, you can use A as a decorator, like @A, and then define a new encodes, which just says x+1. We haven't defined type, so in general, it'll act therefore for whatever you give it as input. Now you instantiate the transform, which is f1 is you call A. Then you pass in 1, and because encode says x+1, what you expect it to return is 2. Now B inherits from A. Since A is inherits from transform and B inherits from A, B is also a transform. So you can do @B decodes. You've added a decodes method to B. Now keep in mind that A does not have a decode, but B, because it inherits from A, and A is the superclass of B and B is the subclass of A, B inherits from A, so B also has an encodes. So B has both encodes and decodes, whereas A only has an encode. So at B decorate, provide the decode function x-1, define f2 is B. I've just explained what I just said. Then when you do f2 of 1, obviously, or not obviously, but because you inherit from A, because B inherits from A, you see f2 of 1 is also 2. So it's executed the encodes. Then you need to, and again, notice something that I mentioned earlier, you just call f2 and it executes encode. The reason why this is important is we will see that as we get into the heart of transform code, we'll see that calling a transform means executing its encodes function. So f2 of 1, when you pass in the parameter 1, it executes the encode function and makes it 2. That's what that is. Test equal f2 decode. F2 decode is that guy. It's 2 minus 1 is 1. That's there. Test equal f1 decode. Here, f1 is transform A. As I mentioned before, f1 does not have a decode. So when it doesn't have the function, what it returns is basically the same value you passed in, and therefore f1.decode of 2 is 2. It doesn't do anything. It doesn't add or subtract 1. And then classically transform f3 of A, and here we've just defined a new transform. It does nothing. So f3 of 2 returns 2. F3 decode of 2 returns 2.0, returns 2.0. Any question on this cell? Okay, so we just execute that. We've seen that transform can be used as a decorator to turn any function into a transform. So for example, let's say this function we define as transform, and it's an integer divide of O, that's F. And then we check that f of 2 is 1, and f dot decode. Now in this case, we have not provided any decode function to this transform. Therefore, expect what the input to be the output, right? So execute that, and we see that there are no errors. Now in this case, let's define also observe that we can use transform itself as a decorator. So add transform and then define a function which is return x of 2, check f of 2 is 1, and check that the decode does nothing because there is no decode defined. Same thing here, it's 2 times x. So when you do the f of 2, it will multiply it by 2, but then there's no decode. Therefore, it returns whatever the input is. Now, this will take a little bit of time because he just downloads one image. I kind of downloaded a bunch of them since it's easier. What we are doing here is just creating a new class called array image, converting just an normal array into that class and adding a show method to it. Not going to go into details of that because those aren't relevant. It's just that eventually you convert, you bring in an image, which is a test image from the data that you just downloaded, and make it of type array image. So once it's downloaded, I just pick one particular image from it, define the class, and make im_t of type array image. That's all I really care about, and the fact that the array image has a show method. Okay, so execute that. Now here's a bunch of transforms, and again, we'll go through it. Ask questions if you don't follow or if things are confusing. You're defining a transform. Notice that in this case, we have defined an encodes, a decodes, and a setup. The setup is just a dummy example, but the encodes, what it does is it says now we are typing the input. So it says if x is a type array image, then negate it, return -x. In decodes, we say if x is of type array image, add 1 to x and return it. And then in setups, if x is of type array image, add an attribute called foo and set it to the value a. This, not very meaningful, but it just to illustrate what setup does when we use it in a transform. Then we instantiate the transform f is a, and then call it on in the array image. Remember, we have made the im_t as array image. So when we check the equality of t, because f basically encodes and returns -x, we expect the value to be negative of im_t. Then when you check f of 1, because 1 is not of type array image, we expect it to return whatever we gave it. So it doesn't execute the encodes. Then we check that t, the value that it's type of t, which is what the encodes returns or this transform returns, is of type array image. Then check that decodes. So when you do f.decode of t, remember what has happened is im of t is what we pass to it. And after the encodes, it's become negative im of t. And when we execute decode on that, it becomes negative im of t plus 1 because it's x after the encode is negative im of t, and then you add a 1. So that's why this is the value that's expected. And then again, we check that decode does nothing when we give it something that where the type doesn't match. And then we execute setup, which just says if setup is called, then ensure that on x, and x that's passed in is im_t, make sure that it has a few attribute and the few attribute is equal to 0. So that's what the test equals does after we execute f.setup. And also again, check that setup doesn't work if the data type is not a match. So if you pass in an array and not an array image, then f.setup of t2, you have to assert that it does not have an attribute foo. Okay, and this is just an illustration of how finally we just say f in order to see what shows up, and it shows up as encodes and decodes are returned with these types. And we'll see the meaning of this as we go through the rest of the notebook. So execute that, and there are no array. errors. Now, here is an interesting twist. Without any return annotation, we get in what is passed in. This is something that he highlighted up above among the behaviors of transforms. So here he defined a transform, decorate the encodes. And again, notice here that we are defining multiple encodes. One encode for type int, another encode for type float. So this is something else that obviously our transform code, as we begin to code up our transform class, will need to support the ability to support methods which then dispatch based on the type we provide, but also can support multiple methods for different types. So you see if it's a capital, by the way, capital int is something that Jeremy defines as a subclass of the traditional int, but with an added show method. So for int, it's an integer divide by 2. If it's a float, it's x plus 1. So define, instantiate the transform, and then check when we passed int2, it's what returns is an integer division of 2, which will be int1. And then when we pass in a normal int, it's not, nothing happens to it. So that's why f of 2 returns 2, because this is only of type, will only execute if it is of type int. What we'll see though is if you define a transform for what I would call a class, and there is a subclass, because the subclass inherits from the superclass, it will run the code. We saw that a little bit up top, and we'll see it again. But in this case, int is a subclass of, or capital INT is a subclass of the regular int. And therefore, if you call it on a regular int, because regular int is a superclass, quote unquote, nothing happens to it. It doesn't execute this code because the type doesn't match. A float, a 2, which means it's not this, but this code, so it's 3. Now, without, here's another interesting construct. Without return annotation, and return annotation means you annotate here in the return portion of the code, we don't cast. That is, we don't say it will be of a particular type. So we are not a subclass of the input type. If we are not a subclass of these types, then you don't cast. And if the annotation is a tuple, that means if you provide tuples here, then any type in the tuple will match. So if, for example, you want a bunch of types to match, you provide them in a tuple. That would mean if X is of any one of those types, it will still execute this. We'll see what happens here. This is just instantiating. Now you see test equal type f of int of 2. And because it is of type int, and that's one of the supported types, 2 will get divided, and what gets returned is 1. 2 is neither type int or float. Here, what we're passing in is not the capital int type, but the regular int, and that's not anywhere in either of these tuple lists or, tuple values. Therefore, it returns what you give it. If you provide it a float, here comes float output. If it's a string A, remember what it does in the definition is string of X plus 1. So string of A, and then you append 1 to it. So it's A1. And then I just played with it yesterday because he doesn't have this among the tests. I was curious, and it seems like it's a dummy thing. He just wants to use it as an illustration, which is why he didn't have it. I wanted to see what happened when you actually provide a list. It converts the list to a string and then sticks in a 1 at the end of it. Kind of meaningless, but he's just illustrating examples.
Srinivas, a question here. So here in the encodes, it's an either or, depending upon that type of whether we are passing int or float, it actually does the operation here. What if we want to actually want to really pass a tuple which contains like the necessary like tuple of int comma float, where you want to really pass tuple itself. Right?
Yeah, and this will still work, right? Because for two reasons. I haven't tried it myself, but I'd expect it to work. And the reason I expect it to work is, remember that as long as you pass in a tuple, your transform works on every element of the tuple. Now, as long as each element is within this tuple types that you provide, it'll execute that. Okay. What it wouldn't, and we'll need to think more about how to do that, is if you wanted something, if you wanted the transform to do something different for an int and for a float, and they are part of a tuple, then you may need to split it and execute piece by piece.
Mm-hmm. Okay.
Do you follow what I'm saying?
Yeah.
But right now, if what you're asking is, can I supply a tuple in which the two values, the first value, let's say, is an int and the second is a float, and as long as you want to do the same operation on both of them, that is, you want to divide by 2, let's say, then this construct will work. Because remember what I told you, that for a tuple, transforms operate on default, by default, on each element of a tuple. So as long as you provide a tuple, it will work, and we'll see this, by the way, subsequently. If you provide a tuple of values, it will operate on each element. Now, it operates on each element and checks the type of each element. As long as you have provided the requisite types in this tuple list of types, it will execute this operation on every element as long as that element is of one of these types.
Okay. Basically, if it should match.
Yes.
Okay.
Right. But as I said, if you wanted something different, you wanted to do something different based on the type, then you'll have to split. As long as you want the same operation on a bunch of different types, if you provide the input to the transform as a tuple and you provide the types in this tuple list, you're fine. It'll work. Okay, let's run this, and we shouldn't see any errors. Okay, now with return annotation none, we get back whatever Python returns normally. So the return annotation, you can either put it here where my cursor is. Can you see that? Right after the return, and like we did here. Or you can just specify with an arrow that says this function is expected to return some value, but with type none, which means it'll return whatever is Python's natural type that it would have returned when this operation is performed on the input X. So F is transform function, test equal types 2, and because you divide it, it's a divide, so it'll return 1, and then because it's a floating point divide, and then you divide a floating point input and it returns a floating point as well. Now, here, the important thing he's trying to highlight with this test is the fact that decodes here has no annotation, right? It doesn't give you any type. It doesn't give you any type on the return part as well. It doesn't restrict X to anything. So what happens in such instances? Remember that what is passed to decode is the output of encodes. So given that the transform, and here's another, here's a variant of transform that we haven't seen before. So far we have seen decoration, and we've also seen the direct inheritance and then override, but we haven't seen passing functions as encode and decode to transform. So this is an example of that. You define a transform, and instead of just passing in an encode, you're passed in the func as encode, and you could call this my decoder. You can call it anything else, but whatever you call it, you pass it in as the decode operator, if you will, to transform. And it takes this as encode and this as decodes in F. So when you pass T is F of 1, then here's what happens. 1 is a normal integer, int, small I. But what's expected to be returned from it, which is the encoding part, is int, the capital I of 1 plus 1 of 2. So int 2 is what you expect the output, which is what you're checking here. Now, when you decode, what is going into the decode as x is capital INT of x. Therefore, by the fact that you haven't said it, or you haven't told decode to return of any, you haven't annotated it, then what it returns is what you give in as input, which would mean that it would subtract 1 from the capital INT, but return it as type capital INT. Is that clear? So the point being here that we haven't provided an annotation. So the annotation it takes is the annotation of the input, which it gets from the annotation that's returned from the encode. Okay. I was just playing with it to say what is F here. Now this is where he illustrates that, okay, split index is a way by which you can ensure that the encodes or decodes operates provided the split index is a match. So let's say we define f dot split idx to be 1. Then if we provide the split idx to be 1, then this will execute, the encode will execute. F of 1 is, remember here, int of x plus 1, so you'll see int of 2. But if we say split idx is 0, and we have defined the f split idx to be 1, then what's returned is whatever you pass in, which means this encode did not run. And it didn't run, not because the type didn't match, because but because the split index is 0. So the type has to match and the split index has to match if the split index is given. In this case, the split index is defined. Therefore, if it doesn't or does match, it does different things. Okay, and then now here's an example of where he shows you what happens when you give it an input to a transform that you give an input which is not a tuple. Now, it took me a little bit to understand, so why the difference? And as I explained, if it's a tuple, this portion of the code where he's actually splitting the list into its constituent elements is not there, if you recall, in any of our tuple related code. So the point being that if XY were a tuple, then this portion of the code that he has coded here would be happening automatically. But now, because it's a list that we are providing as input, we need to provide this code before we return whatever value we want to return. Is that clear? So for example, so what's the difference? We provide, instead of a tuple, we provide a list 1 and 2 as input. So what happens? Remember what has happened here. There is encodes, it's a 2-step process, even though for simplification, he has put it on a single line. This XY, which is the list 1, 2 that we pass into the transform A, splits its elements. So list XY becomes X and Y, which means that 1, 2 become, so 1 is X and 2 is Y. And what is returned is the list of elements X plus Y. So remember, because of that, because of this first part, X is 1 and Y is 2. So X plus Y is 3 and Y is 2. So you see what's returned is 3 and 2. But what is different from passing in a tuple is we have had to add this code. If it were a tuple, then this breaking up or bottom line applying the transform to every element would have happened automatically. And we'll see that below again in more explicit detail. So the rest of it is very similar. Just ensure it's the same. Check below that decodes. Now, again, keep in mind that the output of encodes is what goes in as T, because T is what is provided, and T has now become 3 and 2. So when you provide 3 and 2 and split it, then X becomes 3 and Y is 2. So 3 minus 2 is 1 and Y is 2, which is the reason you see that value. And in fact, one way that you can play with it is remove all my comments, check what you anticipate is what you're getting as he has coded the test. And then again, the same thing, check when split index matches is when you do what you need to do. If the split index doesn't match, input, or more appropriately stated, output equals input when split index does not match. Any questions? Okay, moving along. Here it just says.
I have a question,
Yes.
Do you have do you know of an example where this non-tuple behavior is passed in FastAI?
Is used? Sorry?
Yes, that is used in the, just to get some context.
Where is it used? I vaguely remember when I was playing around with some of his notebook in, but nothing jumps to the top of my mind. I'll try and post something in Slack if I find out. I have this big notion that I did encounter, especially what he does in the very next example. I've encountered a case, I think, where he does what he shows here, which is, see, in this case, what he does is he takes he takes X, and then he applies the transforms to increment the list by 1 for every element. And again, the difference is this would have been done automatically if this were a tuple, but in this case, it's a list. So I vaguely remember in one of his notebooks, now I don't remember why he used a list or a different container than a tuple, but
Okay.
that's
because I think back when it started, he had this item transform and tuple transform defined, and then that changed as it moved along.
correct.
So yeah, that part is something which is very still confusing as to when to use what sort of a thing.
Yeah, actually, the thing that it seems to me is if you want a way to handle every element and you want something different, then you probably want an item transform, because then it treats it as an entity and you can choose to do whatever within that entity you want to do it with. Whereas,
so this name item, what exactly is the item? I think the naming is also very...
yeah, it's a little bit screwed up. It's when it treats something as an item, that's why it was confusing for me to understand. When it treats something as an item, what it means practically, when you get down to it, is you provide the code to handle what you want to do within it for every element, if it is a container.
Okay.
So if for example, it is a list or any other type of container than a tuple, just like I showed here, you have to split it. And just like he shows here, you have to provide what you need the transform to do for every element in the container.
Okay.
Whereas if it's a tuple, that's done for you.
Automatically. Okay.
Automatically.
Right. Okay. So here item is basically dealing with the individual elements of what you're passing in. That's what the item here means.
No, see, that's where it becomes confusing, because when he says in an item transform, then, and we look at the code of an item transform, but I think, and we should probably wait till we see that in order that I don't confuse people by saying the wrong thing.
Right. Okay. Yeah.
Because it is confusing, as you say.
Sounds
but
good, yeah.
Practically what I understood is if it's a tuple, and here is the interesting thing, right? And we'll see this as we go through the code. It handles every element recursively. So if you have tuple within a tuple, it will go through every element of the tuple buried within a tuple. But if it's any other type of container or any other element, now the element case is very simple, right? If you just want it to be a single thing rather than a container, then it will handle it as a single thing. as opposed to a tuple or anything else. So it will just take one thing and handle it as a thing. So that's a simple example of an item. But what happens when an item is a container is the more interesting thing, and it's not a tuple type of container. And that's the example he covers in these two cases.
Okay. Yeah.
Right. So again, here, as I was just explaining, so the L, capital L, which is list, you have to provide the code to handle every element of it. So that's what you do here. And basically that means that 1 and 2. So since you're incrementing for every X, it becomes 2 and 3. And then on the decode path, it becomes, back again to 1 and 2. Right. Now, this is where you begin to see what I was telling, I think, was it money? Was the question earlier, that it'll apply to every tuple, and then, depending on what you provide. And again, here's an interesting example of, a superclass, because numbers.integral covers a bunch of types underneath it. So if you negate an int and return -x, then f is transformed negative integer, and you provide a 1 and it becomes a -1. Now, this is a single entry tuple. That's why it's, a tuple with a comma inside it. When you supply a float, when you supply a float, then, what goes in comes out, because it's not an integer, not of type numbers.integral. And see what happens here. You provide a tuple. The tuple has 3 values. First is a float, second is an int, third is a float. So what it does, and this is, Mani, kind of your question, right? Like, so I'm mixing types here. Now in this case, I want it only applied. I mean, I haven't provided X type to be a tuple, but in this instance, if I had said int and float, then it would execute the negative on both or all 3 of these elements. But now, because it's of type numbers.integral, so it'll only match for the middle guy, and the first and the third people or third values, will remain untouched because they are of type float.
Yeah,
and
this is where it's interesting, Srinivas, because I was actually expecting that, like, if it should, here in this particular case, at least any of the elements in that particular tuple matches, then it actually applies the operation. So I was actually thinking the other way, is that it should match all the elements to be of, then only it should actually apply, but it's kind of like the other way. It's at least
it is any.
Yeah.
I think this illustrates your example that we were kind of talking, that it applies for each element. So it's checking for each element if it's an integral.
Right.
And that's why it passes or doesn't pass when it's applying.
It checks for 1, doesn't match, checks for 2, doesn't match. Now, there's another thing here which is not specified. On top of all this, it will check for split index. So if it isn't split index, none of this it will check. If it split index matches, then it will check for every element of the tuple. Because that applies at the, like, meaning for the entire set of data, like, so, but yeah, to Rekil's point, every element of the tuple is checked against the type, and if the type matches, then it'll apply. But also keep in mind, and we'll see this down below, is you have to be careful about defining this to be the narrowest subclass, because if you define this to be a superclass, it will execute for all subclasses. It will assume that all subclasses match when a superclass is provided as the type of for X. So again, there's no decode, therefore 1 and 2 returns 1 and 2. It doesn't do anything. Okay, so he's just checking the types, ignore that. Interest of, we'll get back to this because this is a little more complex in how you define and change the call method within the transform. It'll be more clear after we are backed away into understanding the code in transform. So I'm going to skip it for now, how to define an in-place transform after inheriting from transform and change it. you can go through it. It's not that complicated to understand, but I'll come back to it. Here, let's again see what happens when the next cell, where you just define B and then defines multiple encodes depending on the different values. And here the return value is made to be none. You pass, but what you return is of type string with a exclamation mark attached to it. So when you pass in a list, for example, the thing that happens is a string of the list with the bang attached to it, because, and why is because of the fact that X doesn't have any constraint on type. So when X is of any type, in this case, X is of type list, then it just takes the list, makes a string of it, and then attaches a bang or an exclamation mark to it. Now, when you pass in a value like 1, which is an int, it obviously does what it's supposed to do for an int. Now, watch, this is a tuple of 2 values. So again, keep in mind that it will execute for each. So it makes it 2 and 3. Now, if you pass it in a string, a single value tuple of a string 1, if it's a string, see what happens is it expected to take X, which is a single string 1, and append another string 1 to it. So it becomes 1, 1. And then a 1.0 passed in within a list becomes a list converted to a string with a bang attached to it. And then because there is no decode among this, a decode of 2, nothing happens. And then I think this one, this is my assessment. Anyone else can chime in if they feel they understand what he's doing here, but I think this is just to show the transform, that you can pickle a transform. So because you're just doing pickle loads, pickle dumps of an instance of transform, and basically dumping it and then loading it returns the same value, which means that you can pickle this transform. So you can store it away. I think that's what he's trying to illustrate. Any comment or questions?
That just returns a true or a false at the end, though, right?
Yes, yeah. But that would
mean that it succeeded.
That because it doesn't return an error, it means pickle loads, pickle dumps.
Succeeded, yeah.
It returned the same value it was passed in. Now we're adding to B the decodes. So keep in mind we have defined B here, and this is again an example of where you can define, you can define an encodes and all that, and then you moving along and you can just use the decorator to add in a decodes for a different type or for a type that already has an encode. So here we already have an encode X plus 1. It becomes we add in a decode which is X minus 1. So then we check that we pass in a 2 and we expect a 1 to come back. By passing a string, then because there is no string decode, then you get back what you passed in as input, right? So that's what you see there. The point here that he tries to emphasize with this example, and you can see why this is a good piece of code to go through, or the tests, is because it illustrates all the different ways that the code actually supports the transform and all the different ways that transforms work. The non-type constraint functions are applied to all the elements of a tuple. So again, a transform decode self returns X plus 1. It's kind of illustrative what we already saw. It's a 1 and a 2.0. Because the type is not constrained, then you see that, first of all, it executes always on all elements of a tuple. So it executes on each of this. But when the type is not constrained, then it does change everything. So here's another way, Mani, that you can do what you were intending to do. If you don't constrain the type and you supply it, as I said earlier as well, as long as the operation you want to do is the same on all types, you need not constrain the type, and then you provide it a bunch of different types, it will do the same thing on all of them. So integer and a float, and you see an integer and a float, right? And it gives you back the same thing on a decode as well. So this is just an illustration that you don't constrain the type. It always executes on all elements of a tuple, but you can get it to do what you want it to do on all elements of a tuple if you don't constrain the type, regardless of type of each element. Then the type constrained functions are only applied to the matching elements, and the return annotations are only applied where they match. So this shows, for example, and you're passing in 3 values in a tuple. The first value is a float, the second is of type small int, and the third is a string. So here we have defined for an int, for a string, and for a capital int, but not for a float. So float should not be touched or will not be touched. But if it's an int, it will return a capital int incremented by 1. And if it's a string, it will append the string 1 and on the way back, meaning if it's a decode, remember, because if an int has been encoded, then the input going in is a capital int. And what you get back in decodes is the capital int integer divided by 2. So now you start and you do the f of start. And what do you expect when you check is a float. So you expect that nothing has happened to it. A 2, which is of type int. Therefore, you expect an int of 3, which is what is given here, and a string 3, which should get a 1 appended to it. So you see a 3, 1. And it also says that, when you decode, the decode is only defined on this guy, int type. So the first and the last values of that tuple, because the type doesn't match, then nothing will happen to them. So you get back a 1 and you get back a 3, 1, but the int 3 is divided, integer division by 2 is the value 1. Is that clear? Any questions? Okay, so that's what happens there. And this is an example I was talking about earlier, mentioning to Raquel that if you define a transform and you have a tuple within a tuple, it recursively operates on every element of the tuples. So for example, we are doing the same, but in this case, it did the 1, then went to this, recognized it was a tuple within the bigger tuple of start. So it checks on every element, and 2 here, because it's an int, will get converted to int 2 plus 1, which is int 3, and then a 3, 1. And when you do a decode, it's the same in reverse. So you get a 1, you get this touched, reduced, integer divided by 2, therefore a 1, and nothing happens to this. Any questions? And
yeah, I have
yes.
a question.
Yes.
I just thought about this now. What if you have like 2 encodes with, let's say they are supposed to dispatch the type floats, both of them, they are performing different things. Is it the last one that will be, called, or the first one? I don't really know. If you have 2 encodes dispatching to the same type but performing different operations.
I couldn't, you were breaking up, so I couldn't fully hear your question. Could you repeat it, please?
Okay, sorry. Can you hear me now?
Yes.
Okay, yeah, I just thought about something. What if you have 2 encodes? They are dispatching to the same type, but they are doing different, they're performing different things. Which one do you think is going to wrong?
Oh, if you're saying you define encodes for multiple types, I haven't tried, or same type, but defined multiple times. I haven't played with it. I would think that it would probably be the last that you define.
The last one, yeah.
That would be my guess, but it should be simple enough to play with. I haven't played with it.
Yeah. I just thought about it.
That'd be my guess, but it wouldn't shock me if it turned out to be the first one either. I just have to go through the code.
Yeah, Tendo, I would suggest not to do that, because the thing was, rather be more explicit, else
Yeah. No,
bugs would creep up.
yeah. No,
I
I would
was just thinking
definitely
about it. Yeah.
agree with the thing you're saying, Mani, but it's a legitimate question
Yeah,
of what
right.
happens, and we're good to know, because if it happens by accident, at least you know what is going on.
Yeah, agree.
So it's a good question. But yeah, I would also agree that better is to stay away from that. If you don't want to end up debugging for hours at a time.
For hours.
That would be a mess. Then you go through class transform here, this typing module type classes isn't extraordinarily clear to me, but I think it's more an inheritance of types based on what you have in typing. Right, so that's what this is. It essentially again defines the encodes, does it for integer, for float, for int, and defines different values. And then, depending on the match, you can decide whether a match happens or doesn't happen. And in this case, it's a decode on a 3 would be, let's see here. So start is a float of 1. And because of float of 1, float, it's multiplied by 3. So it's a 3. Then when you decode, the decode is only defined for an int. So you get a 3 back because nothing should happen to it since a decode is only defined on a int, and t is obviously not an int, it's a float. Then you define multiple values of a tuple, and you do the encodes. Yeah, the first is a float, so it'll be 3 times that. The second is an int. So what you would get is, I think this is where it becomes, if I'm not mistaken, a 3, because the numbers dot integral is what applies, and this 2 turns into a 3, and the 3 is also a float, so it becomes 3 times 3 is 9. And then when you go through a decode, this 3 is an int, and therefore the reduction applies, but the other 2 don't get touched. And I believe if you look at it, an integral is numbers dot integral is probably a superclass of int, and that's why you get that, because it's defined on a superclass to increment by 1, you get this effect of having an encodes available or acting on an int because it's defined on a superclass of int, even if you don't define it on an int. I hope that's clear to everyone. That if you define it on a superclass, it operates on a subclass. But if you define it on a subclass, obviously the superclass is not touched. So you need to define on the lowest subclass that you wish for the transform to operate on. That's the lesson to take away from that. This is the code for the item transform that Rekil was asking about earlier. Again, here, I think a more detailed understanding we'll get once we've gone through the transform code and understood the different pieces of it. So in the interest of that, I'm not going to dive into this piece of code until we have gone through that, but we can still see the application of it, which is identical to what he did when he handled anything that is not a tuple. So you can see that, he says item transform, then he encodes, but then he has the code to split it into its constituent elements. So the key point when you create an item transform as opposed to a regular transform is the item transform treats what you provide to it as a single entity, and therefore if it just operates on that entity as a single element. If it turns out that that entity is a container, then you need to provide the code in order to handle the individual elements. If you don't make it an item transform and you provide, if you just inherit or use default decorator and it's a transform, then as long as the input you provide is a tuple, it'll act on every element of the tuple. Here, it treats what you provide to it as a single entity. And therefore, this is a way to opt out of the behavior where it operates on every element of the tuple. Okay, so that's what the usage of item transform is. So item transform is an example where you want to opt out of the behavior of default transforms, which means that default behavior is for it to operate on every element of the container passed to it. And if you want to opt out of it, you inherit from item transform. So in this case, again, practically speaking, because he has included this code where he splits whatever you give it into its constituent elements, here the 1-2 tuple that you provide is actually split not automatically, but because of this code. And therefore, again, you apply that function to each element. So x plus y, you've split the tuple you provided into 1 and 2, so it becomes 3, and y becomes 2. Is that clear?
Yeah, what is that very first line in item transform mean? A transform that always
Retain equal true?
No, just above that, sorry.
Oh, this one, a comment, a transform that always takes tuples as items. See, the difference is that, so this says that a tuple is not broken up and you don't treat it, you do not automatically process every element of a tuple. Instead, you think of tuple as one thing and you have to provide the code to split it up. That's the way I interpret it.
Okay. So, I mean, putting this in context, you'll always get back a tuple from your data set, right?
Yes.
You kind of expect an X comma Y.
That's mostly what you end up creating, yes.
Right. And so then each X comma Y is treated as an item. That's what you're talking of, right?
Correct.
Okay.
Yes. Okay. And see, sometimes it's not true that that you always get X, Y. If you have pipelines operating on X independently and on Y independently. Right. Because if you're just operating on an X where you're manipulating the X, and then you're operating on Y and manipulating Y to a separate pipeline, then in that instance, you want whatever you're doing to be possibly an item transform because you just want it to operate on that single element that's coming out.
I see. So it's like multiple ways of doing something. You could have achieved the same thing just with type dispatch and a normal transform.
Yes.
Right?
Yes.
Okay.
That's
what got really confusing.
Yes, that is true. But he provides this flexibility, and I'm sure he uses it. And the example he talks about in one of the videos is the fact that exactly what the example I gave, which is in instances where you're operating or using transform pipelines independent, and you have two pipelines, and we saw that in one of the early lectures, one operating on X and another operating on Y before they are combined into a tuple, then you would like an item transform because you want it to operate as single element X.
Right. Okay.
Whereas after it's been combined into a tuple, like you said, which is more common after the things have been combined and coming out of like a data loader and such, then you want to operate on XY, which is why he made it a default, but he gave this option of opting out of it.
Right. Okay. Yeah, that makes sense. Thanks.
Okay, so that's an item transform, and it's an usage of item transform. And he's again here, in interest of time, let's see, it's about 10. We still have 20 minutes. Okay, I think we should be able to get through basics. If you pass a special tuple class, the retain type behavior of transform will keep it. So this is again just saying that if you define your own subclass of tuple, it will retain that subclass. Again, I don't know why he specifically calls that out. And then this is just, again, a match, split index match example. without the split index match, there's no encode, no decode. So this we have seen multiple times. He's just illustrating that happens with tuples as well. And here is a simple example of how you can get a single item, for example, Raquel, and you make it an item transform. And so here is you define an encodes with the single element of X that you return. Now, implicitly, it means that X is a container, because without it, indexing into it would be not very meaningful. But now G is get, you define a transform G, and then G of 1, 2, 3 becomes, so what it does, it gets you the first element. I mean, there are obviously simpler ways of doing it, but he's just illustrating an example of an item transform. And G of capital L, which is of list. Now, in this case, it's a standard list. In this case, it's a, L of, so by doing a get transform, if you will, like this, you can get the first element of any of these types, a list, a capital L, an array, right? And you get a list with one, there, testable type G. Oh, 2 elements, a tuple of 2 lists, A and B, C, and it gets you the first element of the tuple. Right, so that's what this illustrates. The height just says he's just trying to, and then during the lecture, someone asked an interesting question, which is, okay, but suppose I want to read an error if my transform tries to act on some type that I don't support, or so on. So he just illustrates how you can do that. You see in the transform, we just say self X, raise not implemented error. If it's of type int, do this. But if it's not int, if it's of any other type, I mean, you don't really want this kind, probably don't want this as an actual implementation, but just as an illustration. Since in answer to the question of how would you raise a not implemented error or error of any kind if you want to flag on unsupported types, blah, 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 then you could do this, define a transform, put in an encode. You can give it a tuple of types that you don't want it to match, for example, and raise a not implemented error, and then have only supported types here. So therefore, if X, for whatever reason, were to become an of type that you don't want it to do anything, then you can actually raise an error. So you can see that, oops, how did my type get that way? More of a debug mechanism, I would think, than anything else, but he just illustrates how you can do that. So here you see when it's an int, it does a 2, but when you provide it a string, it'll raise a not implemented error. Okay, so we reach kind of the end of the tests that he has provided in transform. So what I'd like us to take away from this is, there's obviously a lot of details, but the conceptual thing we want to implement in our code that implements a transform for fast AI is we need to support 3 functions. We may need to do a whole bunch of other stuff, but at least at the high level, we need to support 3 things. If we call the transform, we need it to execute what is within the encodes method. And it also needs to execute the encodes, the decode, and the setup method on specific types. That is, it needs to execute those 3 methods only if the type provided to that method as an input matches the type that is registered for that method. And we'll get to the details of what that means and how we can do that. So in order to be able to do that and provide the additional capabilities of transform, that is, the transform should act as a decorator, it should accept functions as inputs to encode and decode. Decode should counter what happens or should enable us to go back to what happened from encodes. All of these different types of capabilities that I'm talking about, keep that in mind as we go through the details of how the code that's implemented in the transform class makes that possible. Also, in order to make what I just mentioned possible, it becomes necessary to change the type of class that a transform is. And in order to change the type of class that you define, you need a meta class. That's why he begins to introduce the meta class, meta classes in Python, which is meta programming, and kind of, I think, takes us through that step by step, which is what we'll get to. We'll probably need to stop part of the way into that, but when we start again next week, I'll again refresh that portion because it's kind of new. At least it was new to me, and it still is because I don't do this regularly, but it's fascinating as well. And you learn a lot about changing Python and its behavior, and how when you do certain things in Python, what actually happens behind the scenes. So with that said, let's dive in. So keep in mind what we are trying to now understand is why we need, or what we need to do in order to create this code. I'll show you the actual, in order to create this transform class, which interestingly, as you can see, has a meta class underscore transform meta. So why does the transform class have a meta class which is used to create it? And what is the code in the meta class itself, which is defined here, is something that we will now get into. Okay, but we'll do that step by step, and let's start here. So these are all the different explanations. I've kind of typed it out as we go along, so it becomes easy for us to understand. So let's start with simple classes in Python. When we say class foo, and we, I could have said pass here as well, but a dot, dot, dot in Python is the same as typing pass, which is something else I learned. So when you do a class foo, that means you have defined a class. Now, what you have done by executing this cell is define the class foo. So when you do foo, that means you see that the class foo is being defined. Now, this actually, when you say class foo in Python, is quote unquote syntax sugar. That means it makes this way of describing or creating a class is an easier and simpler way. Something that syntax sugar is something that makes it more tasty for us. So we tend to use it more often, consume sugar, even though it's not as good for our health. But what we are actually doing is defining a type and providing it, or actually using a type constructor and providing it 3 values. The 3 values are the object or the name, so it'll be a string. The basis, this is what the set of classes that this particular class inherits from, and a dictionary. So you pass in 3 things, and it good. As we repeat this, you'll become familiar. The 3 things that you pass into type constructor are the class, the basis, that is the classes this class inherits from, and a dictionary. And the dictionary will become the name, or the dictionary is the namespace of this class. We'll kind of look at what that means. So just to illustrate with another class, and I'm just using foo2 just in order to show, I could have said foo here as well, but just to keep this class separate from the foo class that's already been defined. Foo2 is type and you provide the name of the class, which is again foo2, and you provide the basis from which this class inherits from. Now in Python, all classes eventually inherit from object. So everything is an object. So you provide that as a tuple. We don't inherit, foo2 doesn't inherit from anything but an object. So we just keep it simple and provide the object as a tuple. And then we provide an empty dictionary. So when we do this, this is the more detailed non-syntax sugar version of what we have done in this cell. So if I execute that, what you will see when you compare foo and foo2 by executing this cell, they look similar. What that essentially shows is I have defined a foo2 class by using the type constructor and passing in 3 values. All of that is done through the syntax sugar of defining class foo. Okay. Now let's check, and this is unfortunate, but the term type is heavily overloaded in Python. So stick with me as we go through the various incarnations of it. What is the type of foo? Right? We know foo is a class, just like if we say type of 1 or 2 or 3, which can be integer, and then type of 1 dot, 2 dot zeros will be float. So what's the type of our class foo? Now, interestingly, the type of foo is type. And in Python, if you search for or try to define the type of type, then it returns type. So what this means in effect practically is the fact that type is a class, because type of foo is type and foo is a class. We've just defined that up above. So type is a class, but it's also a constructor which constructs things of type. So that means basically type is a constructor which constructs classes, and classes are of type. So for example, foo2 is of type. And when we say foo2 equals type, and then they pass it the string, the basis, which is just the object, and the dictionary, then you get the class foo2 is defined. And as I think Joseph has illustrated many times before, you can, by typing in this, you can find out many of the attributes which are within the class. As soon as it's created, you see a bunch of attributes that come up in the class. Okay. But of the many attributes in the class, the most interesting one, arguably, is the dunderdict. So when a class is created, among the many other attributes that we saw show up, it has a dunderdict. Now the dunderdict is a somewhat special kind of dictionary. It has weak references and stuff, and these are because you want to garbage collect, blah, 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 when the last reference is gone. Not important for purposes of our discussion, but bottom line is you see that when I execute foo2.dunderdict, it shows what the dictionary is. Now, what is interesting about it is you could actually set an attribute in the foo2 class by, remember we passed in to the type constructor, or when we were constructing this class, we passed in an empty dict. Instead, if we stick in an A string and put in a value of 1, so in the dictionary, we are filling in a string A and providing it a value 1 and defining that foo2 class using the type constructor, then let's see what actually happens. What actually happens is the fact that in the class dunderdict, you now begin to see the attribute A, right? So that's what is going on when, again, there is a syntax sugar way of doing this more complex thing that we just did here. And that is to say class foo2 A equals 1. So when we do this, which is what most of us are used to, which is specifying a class and then giving an attribute in the class, this is the syntax sugar way of actually sticking in an attribute A in the foo2 class during construction. And you can do that after or before. And you do this, which basically means in the class foo2, you have now instantiated in a equals 1 attribute. So now again, if you look at the dict, it'll have the a equals 1. So what this means is saying a equals 1 in the cell above right here is the syntax sugar way of defining an attribute in the dunderdict attribute of the foo2 class. And which means that in the dunderdict, we now have a string A with a value 1. And that's what that means. And again, the access way, syntax sugar way of accessing it, accessing the value, is just to say foo2.a. But that, in effect, Python behind the scenes translates it to foo2.dunderdict a, which is how it gets that attribute, right? So that's kind of what you see happening. And why is all this relevant? I mean, why did I go through all this definition of type and illustrate all this? Because when we define and when we begin to define a meta class, we're going to replace the type constructor with our own constructor. So that's what a meta class is. A meta class is replacing the standard type constructor in Python and changing some of its methods of the type constructor with our own methods, so we can change the class that it creates, that our constructor instead of the type constructor creates. So that's what this explains. So we want to use some other constructor to construct our classes. So we want a different type of constructor to construct our transform class. And how do you do that? You do that by saying a meta class equal to something and providing the name of the class that you want to construct your resulting class. So for example, if you want to construct a class called myClass, remember in our eventual example, this would become a transform. But in the toy example we want to use to illustrate it, we are using myClass. And we use, instead of a default, which would have been type, and therefore we wouldn't have had to have provide anything. In this case, because we want to change the type constructor, we say meta class is underscore transform meta. That means in order to create the my class, use the meta class that I give you, which is underscore transform meta. So now you could typically create, and we'll go through an example using a very simple example, which is this underscore m class. And you could create the class, which is the underscore m, or we could create the underscore transform meta in our actual usage from scratch. But what we typically do, as in anything else in Python, is because you want to change, remember what we are after is to change the type constructor. And in this case, what we do is we inherit from type and then we change things which are in it. So we change the methods of the type constructor. So we inherit from type and change what we need to change. So we subclass type. And again, remember that the three things that type takes as input are the name of the class you want to construct, the basis, and the dict. So thing to take away from this brief discussion is the fact, and I'll provide a bunch of links in Slack that you can kind of spend a lot of time understanding metaprogramming and meta classes in Python if you wish to do so. But the key takeaway that you need to have is the fact that a class defines or instances or creates instances, whereas a meta class is something that we use to create a class itself. So in order to build a class, you use a meta class or to create a class. And a class that's created, normally this is what we do, is we use class and then create instances of the class. So let's use an example, use a very simple example of a meta class without changing anything in it. So what we're doing now is just saying underscore m is of type, So that means we are basically saying we are not changing anything in it. And within this, there's this method called dunder new, and we'll learn more about it as we go through the rest of the lecture. You provided the first input to it has to be a class because that's what we are building. And then we provide the three things that we talked about, the name, the basis, and the date. And we say return super, and the super here is just calling into the type constructor, new, dunder new, and then you provided the class name, basis, date. Now, because you're doing the same thing here, you haven't changed anything. You just used used underscore m instead of the default type, okay? So we haven't changed anything. So we should expect nothing to have changed when you use meta class underscore m to create the class t. Now, the interesting thing is obviously here we haven't changed anything, but once we begin to change it, then we will see that the class gets constructed with changes in it, right? Now, why is this again important or relevant? Why are we talking about this? Because eventually what we are after is that any class that inherits from the type of class that we create. So here we are calling it T, but let's say this becomes transform eventually. Then we want all of the classes that inherit from the transform class to have the desired behavior. And what behaviors the classes inheriting from transform need to have is defined by using a meta class. But we'll see that as we unroll the rest of the chapter, right? And this change of behavior of the class, which is that depending on the type it dispatches and so on and so forth, that can be achieved only by making changes in the meta class. Now, so far though, we have just defined underscore m to be the same as what a typical type constructor would do. So if we execute this and define a meta class as underscore m, remember we have made no changes. Therefore, when you look at the class T, it should look much like foo or foo2 did. It also would have this dictionary, which obviously is an empty dictionary. Now, let's begin to make some small changes to the meta class and see the change that begins to happen in the class that we are defining. So if all I'm doing here is adding this one line, the print line, and read it. It's an interesting print statement because it says, I print this when I'm defined, so that dunder new is run when the class is defined. And then I just return the same thing. So that's the one line change that I made to the meta class underscore m. That's the only change compared to the traditional type constructor. Now, interestingly, when we define the class, see what happens is the print statement is executed. So what this means, interestingly, is dunder new of a meta class is executed when the class is defined, not when the class is instantiated. This also leads to, at least for me, an interesting understanding or grasping of what Python does. What Python does when we defined or when we did this syntax sugar thing of class foo2, where was that? Up here, class foo, or or we could say class foo2, is it actually runs dunder new, creates a class and provides it to us, which we then use the init constructor to initialize it. So what I didn't grasp before was I thought init constructed the class, but init actually just initializes the class. The dunder new creates the class, gives us the class back, and that is then updated with the init constructor. Init is also called a constructor, but it actually initializes the class. So back to where we were, that's illustrated here very clearly because dunder new is executed as soon as the class is defined. Okay, so that's what I highlight in the next two statements. We will kind of revise this piece next time, but I just want to point out two things before kind of ending this session. Since we're about 10 minutes over, we'll take about 5 more minutes and then we'll be done with this. The point I want to make is if we look at the underscore transform meta class, right? What we will see is we are replacing 3 things in the type constructor. We are replacing dunder new, we are replacing dunder call, and we are replacing dunder prepare. Now, the interesting aspect of replacing these 3 things, and if you want to understand much more about the details, you can kind of go through these links. This data model of Python is what is critical. Moreover, you can go through all of the document for the details, but more specifically, if you look at what is relevant is customizing the creation of the class, because that's what Jeremy is after in this particular case. He's after creating or using a meta classes in order to define new types of class, which is a transform class. And the transform class is a new type of class because we want Python's behavior to change and dispatch based on the type of its input, which is not what it does otherwise. So the most important thing about this, and you can go through it offline in more detail, is one of the first things that you need to do. The method resolution order is what MRO stands for, and that is essentially having more to do with multiple inheritance. Not extremely relevant to our discussion here, but you can follow up on that through some of the links that I'll provide later. The important thing is preparing the namespace of the class. That's what we need to do, which is in fact what we do by providing the dunder dict to the class. And then once we have prepared the namespace, which is basically the list of attributes and other things that are within the class, then we can call the class. And you can kind of further and further dive into the details using any of these links. If you want to understand more about what a namespace in Python is and stuff, then you can go to any of these links that I've provided below as well. The point is that if we look at the transform meta, what we are doing based on our earlier discussion is we are inheriting from type. That means we are wanting to change the type constructor. Now, what 3 elements of the type constructor do we want to change? We want to change the dunder new. We'll kind of understand what changes we want to make to it later. But at this point, what's important to realize is we want to change the dunder new of the type constructor. We want to change the call of the type constructor. And we want to change the prepare method of the type constructor. So those are the 3 things we change in the type constructor transform meta, which is our meta class. Okay, so we'll restart from this point and get into the details of what we are changing and how and what those changes enable a transform class to be built, and why building the transform class in the way he has built it enables us to do the thing that we want the transform class to do in the remainder of the lecture, which I hope we'll complete next time, but if not, it might take another class as well. But again, as he says, one of the things which is kind of important to take away is, while the first part of our lecture was kind of interesting from an application standpoint, you need not understand any of this stuff if you want to use the capabilities of FastAI library. But there are 3 reasons why I think it's very interesting is because A, it provides me with the ability to understand the library knowledge complexities, also makes a better Python programmer since I understand a lot of how it works. And it also enables me to become better at debugging the capabilities. Okay, and we'll start, in fact, just for some redundancy, we'll start with the definition of the class and the meta class next time, so we can kind of refresh our memory as we go further into the details of how a meta class works, how the transform meta class is coded, and how that results in the transform class that we really desire. Any questions? Everybody asleep now?
No, we're awake. Thank you so much, Srinivas.
Yeah, it's not a question, but can you please share this notebook so we can like review, especially those links?
I'll post it. Be aware that because this one and the other one, which is the type dispatch, he kind of goes back and forth between these two notebooks. I continue to edit them as I go through the subsequent lectures. So anticipate further changes, but I'll post this one for sure after the class is done.
Hey, Srinivas, this is really great. I'm wondering if you would consider making a Git repo with all of the work that you've done, and then you can continue as you can just continue working on the things and put them in the Git repo as you finish them.
Yeah, sure. I'll look into that.
That would be great, because then we'll all be in one place and be very convenient.
Yeah, I'll look at creating that and putting that on Git. Yeah.
Yeah, this is a really nice explanation. Really, really nice.
Yeah, going through it and piece by piece and walking through it multiple times, at least, as I said, it gives me a better understanding and enables me to use techniques or tips that I've never considered or done before. So kind of removes the fear, if you will, of diving into code.
Yeah. Oh, thanks, man.
By the way, before we break up, I'd like to mention, you probably already know this, everyone, that Jeremy's book is now available on Amazon, and it's already shipping. So if you've pre-ordered your copy, it's either there, you've either gotten it already or it's on its way. But if you've always wanted to order a copy, it's now available.
Cool. So I'll post it on Slack, and as to Joseph's comment, I'll create a Git repo and start dumping my versions of the node